Okay, so first of all, I would like to thank the organizers for and giving me the opportunity to talk here. So the topic of the talk, as you can see, quantum symmetry of graph sister algebras and quantum symmetry of general sister algebras. One can think of it as a non-commutative analog of group symmetry of compact Hausdorff topological compact Hausdorff spaces. Okay, so I will elaborate on these things. In this talk, 50%, roughly half of the talk will be just introducing the basic concepts and sort of put our work into context, and the rest half will be just mentioning few results that we got out of this project. And this talk is based on a project jointly with Professor Arno Mondal from Presidency University, Calcutta. Okay, let's begin. So, what are sister algebras? I think sister algebras are fairly well known, particularly to this audience. I think still, let us recall what is a sister algebra. Sister algebra is a Banach star algebra with the norm satisfying the sister condition. The norm of A star A equal to norm A star. And in this talk, we shall talk about only about unital sister algebra, which are analog of compact Hausdorff spaces, topological compact Hausdorff spaces. Okay, and typical examples include Cx for any compact Hausdorff space with the usual norm, subnorm, and usual star structure, the complex conjugation, and Vh for Hilbert spaces, separable Hilbert spaces. Let's say H. Yeah, typical examples of unital sister algebras. And let me mention the theorem, Gelfand-Naimark theorem, that any commutative sister algebra, in fact, is isometrically isomorphic to Cx for some compact Hausdorff space. And from this theorem, actually, when one would like to think a general sister algebra, not necessarily commutative, as analog of compact Hausdorff space, let's say non-commutative compact Hausdorff space. But although we won't have really such a compact Hausdorff space underlying, so that we can realize a non-commutative sister algebra as some Cx, obviously, because Cx is commutative. We cannot do that if the sister algebra is non-commutative. Nonetheless, we think any non-commutative sister algebra as the non-commutative analog of compact Hausdorff space. Okay, and for any general sister algebra, be it not commutative or non-commutative, what we have that we can at least faithfully represent it over some separable Hilbert space. Okay. So these are sister algebras, and our object of study, sort of, for this talk at least, is graph sister algebras. So let me introduce what are graph sister algebras. Graph sister algebras are sister algebras, unital sister algebras. It's a particular class of sister algebra generated by partial isometries. And of course, from the name you can guess that, of course, graphs have to be involved in the definition of such sister algebras. Now, given a graph, we can associate a unique unital sister algebra generated by partial isometries. How we can do that? Let me quickly tell how we can do that. Kuhn's algebra is a particular example of a graph sister algebra. So let me explain Kuhn's algebra. How does it come from graphs? Because Kuhn's algebra is familiar to almost everybody, I think. So let me talk about Kuhn's algebra with n generators. And this is the graph. There are n many leaves, n many, let's say, edges. All are loops and only one vertex, so to say. Okay, so corresponding to each loop, associate a partial isometry. So we have n many partial isometries, and we have a vertex. Assign a projection on that vertex. In this particular case of Kuhn's algebra, the projection will be identity, and how the initial and final projection of these partial isometries are related to the graph. These are related precisely by Si star Si equal to identity and summation SI star is also identity I from 1 to n. So for general graph, suppose we have some graph, then for general graph, what you have, you assign partial isometry to every edge of the graph. We have edge, and this SI star, and to every vertex you assign projections to every vertex, and this is target EI. Target meaning the usual target. You have a oriented edge so that you have source vertex and target vertex, and this is equal to PV such that V equal to source of E. Okay, these are graph sister algebras. Given a graph, you can associate uniquely what is called a graph sister algebra. Okay, so this is our sort of non-commutative analog of topological space. So once we have this non-commutative analog of topological space, what would be the non-commutative analog of group symmetry? As I mentioned in the beginning of the talk, this is, we can think of like the study of group symmetry over topological space, compact topological space, non-commutative analog of that. So what is the non-commutative analog of, let's say, compact group? Okay, so the non-commutative analog would be compact quantum group. So what is a compact quantum group? Again, suppose we are given a compact group, forget about compact quantum group, given a compact group, we can encode the group operation in the commutative sister algebra CG with this coproduct map delta from CG to CG tensor CG. This is a topological tensor product. This is not algebraic tensor product, but this is technical details. For the moment, we can forget about that. This is topological tensor product of sister algebras, and this can be thought of as C of G cross G, and this coproduct is defined using the group operation delta F of G1 G2 equal to F G1 G2. Then associativity and the existence of inverse and unit are encoded in this following two conditions. This condition is called co-associativity, and this pair density condition actually encodes the existence of inverse and unit. Then one can obtain the non-commutative analog of the compact group called the compact quantum group by replacing the commutative sister algebra CG. You replace the commutative sister algebra CG by any non-commutative sister algebra, let's say Q, and take these things as your axiom, meaning that there is a unital sister homomorphism delta from Q to Q tensor Q, and satisfying the co-associativity. Those things make sense for in case of non-commutative sister algebras also, and this we take as the definition of our compact quantum. Okay, fine. So what are some of the examples of such compact quantum group which are not, of course, group? We know that given a group, of course, the sister algebra, we can make it a compact quantum group by defining the coproduct and the span density, defining the coproduct using the product rule of the group. Now, what are some genuine sequences which are non-commutative sister sister algebra non-commutative, let's say? Okay, so first of all, let us recall the permutation group. This is just usual permutation group Sn acting on endpoints. Okay, then we can, I mean, think the commutative sister algebra, the function algebra over Sn as a finite dimensional sister algebra generated by characteristic functions chi ij, right? These are the functions which take value 1 on the permutation, which takes I to j, and 0 on other permutations. Then we have the following algebraic relations among the commuting elements chi ij. These are functions, okay, functions on Sn, so they have to commute. So these are commuting elements, and we have these algebraic conditions that they are actually projection in the commutative sister algebra CSN, and also satisfying this condition. And one can check that in that case the coproduct, which will be from CSN to CSN tensor CSN, is delta chi ij equal to summation chi ik tensor chi k. Okay, so this is the standard permutation group, nothing quantum about it. Now what one can do, what we have been doing from the beginning of the talk, So one can think of a sister algebra. One can actually drop the commutativity among these generators chi ij. Okay, keep rest of the conditions, but just drop the commutativity. Then we will have some symbols uij such that they are projection uij square equal to uij equal to uij star, and this particular two conditions resembling these two conditions from this chi ij's, and take the universal sister algebra generated by these symbols. Of course, one has to prove that there is such a universal object, but take the universal sister algebra generated by these elements. These are non-commuting. That's all. Sort of we have made the generators chi ij free, algebraically free. I mean, first of all, algebraically free, then we quotient by the ideal generated by these things. Okay, so this is the underlying sister algebra. Once we have this underlying sister algebra, then one can define the co-product on the generators by this formula. Of course, one has to check that this is well defined. Again, see the similarity from the previous co-product delta chi ij, and this is called the quantum permutation group, sort of the non-commutative analog of the permutation group. And this is again, this doesn't arise from a group, of course, because this is non-commutative as a sister algebra. And what is very interesting is that this Sn plus is quite big in the sense that for n greater than equal to 4, this is actually infinite dimensional as a sister algebra. And if you take the classical CSN as a sister algebra, whatever n you take, you know this is finite dimensional as a sister algebra, right? So this is quite different as a sister algebra from its classical counterpart, let's say. Okay. So once we have this Sn plus, we can similarly obtain sort of free version of the classical unitary group, right? So what would be the free version of the classical unitary group? This will, as a sister algebra, it will be universal sister algebra generated by symbols uij, ij from 1 to n, such that both the matrices uij and uji are unitary. This is the relation, and with the this following co-product on generators delta uij equal to summation uik tensor ukj. You can check that classically it happens if you take the classical unitary group on in un. Okay, so these are examples of CQG that are relevant to us for the moment. Okay, so now we have our analog of the compact Hausdorff space, that is graph sister algebra for this talk for us. This is graph sister algebra, the analog of compact Hausdorff space, and we know what is the analog of the group symmetry. It is the compact quantum group. So we have introduced the compact quantum groups. Now we have to make sense of what do we mean by such CQGs, compact quantum groups, called CQG in short. What do we mean by such CQGs acting on such non-commutative spaces? So here is the non-commutative analog, and again we motivated by its commutative counterpart, then we define the non-commutative analog. So recall, so if a compact group G acts on a compact Hausdorff space X, let's say, then we can encode the action in terms of the function algebras over X as well as the group. How to encode that? We have a map alpha from Cx to Cx tensor Cd. Again, this is a topological tensor product, not algebraic tensor product. And this we can identify with C of X cross G, and one can check. This is the sort of using the group action on the space. One can define alpha F, and this lands here, the image of alpha, and the coaction satisfies these two conditions. These two conditions completely encodes the coaction, the group action information of the group action, the fact that G actually acts on it. So as before, now liberate both the space as well as the group. You replace Cx by any particular sister algebra and replace Cg by any compact quantum group, not necessarily function algebra over a compact group. And you take these things as axioms, like what do we mean by a compact quantum group coacting on a sister algebra Q? We have a unital sister homomorphism alpha from, let's say, a sister algebra A, replace Cx by A, replace Cg by Q. So we have alpha from alpha A to A tensor Q such that alpha satisfies these two conditions. Here also you have to replace Cx by A and Cg by Q. Okay, so this is a similar philosophy, the recurring philosophy, and I think many of you already have seen this in some of the talks, previous talks. Okay, now as you can probably guess that Sn plus is a generalization of Sn. The next question is, can Sn plus really coact on finitely many points? And it turns out that indeed for n point space X, if you take your sister algebra to be Cx, then Sn plus, which was fairly large, larger than classical Sn at least, that coacts on X, coacts on the sister algebra Cx maximum. Okay, and in so what we have is that now, even if you are given only n point space, the classical n point space, then we have a generalized larger symmetry in some sense, and which actually contains the classical symmetry group. Okay, so I want to elaborate on what do we mean by contain the classical symmetry. That will take us to some more technicality. We don't need that at this moment. Okay, so yeah, so we see that this thing happens. This is very interesting, that even if you are given n point space X, then there is a large object compact quantum group that coacts on Cx maximally. And I would like to just mention that this typical thing actually doesn't happen when we have in place of n point space, when we have some compact geometric objects, okay, so to say compact Riemannian manifold. Then all we have the classical isometry group coacting on a classical Riemannian manifold isometrically. We don't have a real, I mean, genuine, so to say, compact quantum group which is non-commutative as a sister algebra coacting on that thing. So this phenomena actually typically occurs on discrete setup, or even in continuous setup also it happens, but somehow it doesn't happen in your geometrical setup. Okay, okay, fine. So now, since we have Sn plus, now what would be the generalization of automorphism group of finite graph, right? We can think of n point space as a graph, a very trivial graph that only you have only n many vertices and you don't have any edge among them. So can we generalize, once we have the sort of coaction of Sn plus on n point space, can we generalize to, some coaction on finite graphs in place of n point space? And indeed we can do that. Again, we would mimic the classical notion of group action on graph. What is a group action on graph? There's some those partitions which actually, if you think partition, so those permutations, if you think permutations as permutation matrices, those matrices you allow which commute with the incidency matrix of the graph, right? That is known, that is how group action of graph comes, and we can generalize it. So what would be the generalization? Given a finite directed graph gamma with n vertices, say, without multiple edges, this is a technical condition. We need that without multiple edge to talk about quantum automorphism group of finite graph, because of the classical, the reason is again classical. If it has multiple edges, we don't know what to do with those multiple edges. Okay, so quantum automorphism group will be a quotient of Sn plus, like the quantum, the classical automorphism group of graph. It would be a quotient of Sn, of course. And how do we take the quotient? We take such a quotient that forces the matrix A, Uij. If you recall, Uij is the classical counterpart, the non-commutative counterpart, the classical permutation which maps the vertex I to j, and this matrix commutes with the incidency matrix that will give the quotient of Sn plus. So this is the sort of quantum automorphism group of finite graph. Okay, and by what we know classically, the graph is vertex transitive if chi ij is non-zero, right? If there is a partition which there is a permutation which takes I to j. So from that analogy, we say that a graph is quantum vertex transitive if Uij is non-zero for all ij. Okay, And this is just a side note that the Poincare series of quantum automorphism group of finite graphs that have been computed by Banika. This is quite interesting. He had used planar algebra techniques to compute such things. So, yes, so this is just side. So now, how to define a quantum automorphism group of a general sister algebra? Let's say we have a general sister algebra. So far, we have seen quantum automorphism group of finite spaces like endpoint spaces, and even if we have a graph, this is also finite space, endpoint space, but we with some edges and all. We know the quantum automorphism group, how to get the quantum automorphism group. Now, suppose we have a general sister algebra. Then what is the quantum automorphism group of a sister algebra? Can we define such a thing? It turns out that we define, just we have to pick the right language. What is the language? That suppose given a sister algebra A, one considers the category of compact quantum groups coacting on A. We know what do we mean by CQG is coacting on A for any sister algebra, right? So we take the category of compact quantum group coacting on A. Category meaning the objects are compact quantum groups and morphisms are CQG morphisms. I am taking elaborate on what do you mean by that. If you have such a category, you can always consider such a category. Then the quantum automorphism group of a sister algebra, one would like to define it as the universal object in that category, meaning the largest such compact quantum group that can coact. That should be your quantum automorphism group from our classical intuition. Like classical automorphism group, you can think of universal objects in the category of groups acting on spaces, right? So, and indeed, Sn plus actually came like that. So, Sn plus, what is Sn plus? It is the universal object in the category of compact quantum groups coacting on Cx, where x is endpoints. Okay, and as you can already guess, the existence of universal object in such a category that might be an issue. Well, for endpoint space, it is not an issue. The universal object always exists, but if you have any general sister algebra, it turns out that such existence of such universal object is not actually guaranteed. Okay, okay, fine. And what the next question is, what do you do in that situation when the universal object might not exist? And indeed, it doesn't exist. Even for, if you take your sister algebra to be MNC, then if you consider the category of compact quantum groups coacting on MNC, then indeed, I mean, it doesn't exist. The universal object doesn't exist. Okay. So what do we do? In that case, that is also done by Suzhou Wang. By the way, I have forgot to mention that these things, this quantum permutation group, this thing was introduced by Suzhou Wang in his seminal paper. And yes, so, and in that paper, he actually noticed the problem with the existence of universal object, even in the case of a simple sister algebra like MNC. So what he did was that he considered a restrictive category. What is the category? The category is same, the almost the same, that category of CQG is coacting on the sister algebra. And in case of MNC, he noticed that if you restrict the category of CQGs coacting on MNC, and moreover preserving the trace of MNC, then the universal object exists in that restrictive category. So this is quite generic when one studies quantum automorphism group of any sister algebra. Often the universal object would fail to exist. In that case, one would restrict the category and one would choose a state on the sister algebra and take the category of CQGs, which not only coacts on that sister algebra, but also it preserves the state in some sense. What is the precise meaning of preserving the state? Let me write it down. I will explain what I mean by these things. Tau f1. So your this was a tensor CG, and one can see like this, and if tau is a state on a, this thing makes sense. So This is what we mean by state preserving. Okay? So it is standard by now to assume some state preserving category and prove the existence of universal objects. Okay. Okay. So with that, now we have the tools sort of. So our analog of compact topological space would be graph sister algebra, and we would study quantum symmetry of graph sister algebra. Okay. And again, if one considers the category of compact quantum groups coacting on graph sister algebras, the universal object again would fail to exist. So we would have to assume some state preserving property, I mean some state preserving category. Okay, now the thing is that the state space is too large, right? If you are given a sister algebra, then I mean, what are the states should I take so that we can talk about state preserving category, right? So this is a problem. But it turns out that graph sister algebras have a well-studied state. They are called KMS states. So we have restricted our attention to the KMS state preserving quantum automorphism group, let's say. And the goal of the project was like to see if such study can enrich the field of quantum groups. Can we get something new in the field of quantum groups, or maybe that can say something about the graph sister algebra itself, who knows. So we started that project, like then I will report some of the things that we have found so far. So as I mentioned, we shall focus on KMS state preserving category. So let's recall what are KMS states on graph sister algebra. So KMS states are analog of what are called Gibbs state for matrices, MNC. We can talk about KMS state on a sister algebra, on any sister algebra, provided the sister algebra has a dynamics. What is the dynamics? This is a map gamma from R to OT A. A is a unital sister algebra. Okay, so this is called this we call the dynamics. This we mean that the sister algebra admits a dynamics, let's say. So provided that a sister algebra comes with a dynamics, then a state on that sister algebra is said to satisfy KMS condition at an inverse temperature beta. So this terminology, temperature and all this comes from Gibbs state. So we say that a state satisfies the KMS condition at an inverse temperature beta if tau of AB equal to tau of B gamma I beta A. So tau is not quite racial, but almost racial. The non-raciality is actually dictated by the dynamics. You can see this non-raciality is dictated by the dynamics. Again, this gamma is defined on R initially, but there are technical things here going on. I don't really explain those technical things. So you have to have an analytic continuation, then you can talk about such equalities. So this equality should hold. Then we say that this tau satisfies the KMS condition at an inverse temperature beta, and AB, this AB is in some dense subalgebra called the subalgebra of analytical events. These are technical things, so I won't talk about these things. And what is I won't say interesting, but it is a fact that unlike in MNC, what happens in matrices, the Gibbs state, these KMS beta states, they exist uniquely at every inverse temperature. Okay. First of all, they exist at every inverse temperature and they exist uniquely. And however, for any general sister algebra, it doesn't happen. It might happen that KMS states don't exist at a given particular inverse temperature. It might happen, and although even if it exists, they are generally quite far from unique. They are not unique in general. Okay, so now we know what are KMS states on any general sister algebra. Now we want to talk about KMS state on graph sister algebra. So for that, we first needed dynamics on graph sister algebra, right? Then we can talk about KMS states. And by the way, the graph sister algebra, one of the main things about graph sister, one of the good things about graph sister algebra is lot of sister algebraic property and all, they are actually encoded in the underlying graph, on the underlying combinatorial data. So it makes life easier that you have some handle on the study of those sister algebras. And similarly, I mean, it turns out that the existence of these KMS states with respect to natural dynamics, you can sort of define a natural dynamics. One can check that if you have, let's say, gamma t of Si, remember, graph sister algebras would be generated by partial isometries Si. Each edge, you can associate partial isometry to each edge. Okay, so this is defined by e power it. Oh, sorry, this is bad connection. Say Sk. This is complex number I. Okay, so this is the natural dynamics, and one can check that this actually I mean, lifts as a dynamics on sister gamma given any gamma. Okay, so corresponding to this dynamics, one can talk about, of course, the KMS states. Now the question is, at what temperatures KMS state exists, and even if they exist, are they unique? These questions are natural and they are already studied and fairly quite detailed. So it turns out that given any graph sister algebra sister gamma, suppose you have a gamma, so you have a unique graph sister algebra, we denote it by sister gamma. So the spectral radius, if we denote the spectral radius of gamma, meaning that spectral radius of the incidency matrix of the gamma, not the graph, but the incidency matrix, then log rho d, ln rho d is said to be the critical inverse temperature of the graph. Okay, of the graph sister algebra of the graph, and once we know that this is the critical, why it is called the critical inverse temperature, that is not really the issue of this talk really, why it is called critical inverse temperature, because beyond that temperature something happens and below that temperature something happens. So this is the critical temperature sort of. Okay, so it then this sister gamma, with this gamma and the natural dynamics, it has a KMS ln rho d state. This is the critical inverse temperature ln rho d. Sorry, this is ln of rho d. No suffix. Okay, so KMS ln rho d state tau sister gamma has a KMS ln rho d state. Now, if and only this rho d, the spectral radius, is actually an eigenvalue of the incidency matrix. That is what I mean by the underlying combinatorial structure actually helps in studying graph sister algebra. You can see that this, I mean, just by looking at the matrix and its spectral radius and all and eigenvalue problem, you can decide whether KMS state exists at a given temperature or not. So this is a plus, right? So okay, and n is a probability measure on the set of vertices, meaning that you take some non-zero values adding up to 1, because it has to be a state first of all. Then the KMS state will be given by this formula, tau s mu star equal to this. This is the formula. What is s mu star? So this is not really one particular partial isometry. This is a collection of partial isometries concatenated one after another. If you have a path, then you can talk about these things, and these are actually dense subalgebra of the graph system, right? Suffices to define a state on this dense subalgebra, and this is the formula. Delta mu nu, when you have the same path, only then this survives, and when it survives, it is given by this formula. And this S mu, this target of S mu will mean the target vertex of any path. Okay. Mu is a path. It's not a particular edge, it's a path, so target is a vertex, and we have a probability sort of measure on the set of vertices. So this is the formula. This is given by that formula. And again, as I mentioned, in general, the above KMS state, even if you have the existence at inverse critical temperature, it is not unique. It is far from unique for graph sister algebra. For example, if you have a graph with this kind of graph, we can draw the picture somewhere here. This is the graph. Let's say this is one vertex. This is another vertex. This is another vertex. So there are n disjoint vertices, and each vertex has a loop. Okay. If you take this graph, the corresponding graph sister algebra, and you can check the identity will be the incidency matrix. This is easy to check, and so that your spectral radius is 1 and the critical inverse temperature is 0 actually. And at critical inverse temperature 0, there are infinitely many KMS states. Okay, so it is far from unique. Any probability measure on set of vertex will give you such KMS state, because identity has this whole Rn as eigen space. So okay, so this is far from unique. And but for a particular class of graphs which are called strongly connected graphs, the KMS state is actually unique. What are strongly connected graphs? Roughly speaking, you can start from any vertex and you can go to another vertex by some path. Those are strongly connected graphs. So if you have graph system algebra corresponding to strongly connected graphs, you have a unique KMS state at the critical inverse temperature. And an example of strongly connected graph will be very trivial example. The Punj algebra is the graph of Punj algebra is strongly connected, and that is why, I mean, that is one reason that Punj algebra has a unique KMS log n state, that we know that it has a unique KMS log n state. Okay, fine. Now let's talk about quantum symmetry at the critical inverse temperature. So we shall talk about quantum symmetry as the universal object in the category of compact quantum groups coacting on graph system algebras and preserving the KMS state at critical inverse temperature. And again, the KMS state, the choice of KMS state is not unique. So we cannot talk about the quantum symmetry at the critical inverse temperature, because if you vary the state, your universal object will vary, that you can already guess. But as I mentioned, for strongly connected graph, at least you can talk about the quantum automorphism group. But nonetheless, it makes sense to, I mean, see the universal object in such categories. Okay. So, and this is again technical, why we are taking this. This is finite, graphs are finite, directed, and without sinks. This is technical. When we have to take without sink to talk about the existence of KMS states and all. Okay, so we have, suppose we have such a graph, a finite directed graph without sink with n edges, then sister gamma will be generated by n partial isometry S1 S2 Sn, and we take a graph such that the spectral radius is an eigenvalue of the incidence matrix, so that it has a KMS state at, it has KMS states at the critical inverse temperature ln rho d. And this is quite a large class of graph, that those graphs which have spectral radius as an eigenvalue. For example, every regular graph has it, belongs to this class, and any strongly connected graph will also belong to this. So we have a fairly large class of graphs. Okay. So now, given such a graph, let's consider the category. We denote the category by C gamma tau KMS. Gamma will remember that we are talking. We are working with the graph gamma. Tau will remember that we have chosen a particular KMS state. The KMS, of course, will remember that we are working with KMS states at the critical inverse temperature. Okay. So what is the category? The objects are compact quantum groups having a KMS state tau preserving linear coaction alpha on sister gamma. What do we mean by tau preserving? We already have sort of mentioned what should we mean by a state preserving coaction. But what do we mean by linear action? We say that alpha is linear if this condition holds. Alpha Si, that means alpha preserves the set of partial isometries. That is the linear. That is what we mean by linear coaction. So we are concentrating on the category of linear coaction, the categories of compact quantum groups which have linear coaction, and it preserves a KMS state at the critical inverse temperature. Okay, and then one can prove that universal object exists in the category, and this is, and the proof is quite generic. I mean, it is already there in the literature in some sense. We had to adapt the technique. The idea is to embed the CQG in a large known CQG. That is the idea, but you can look in the references that I will mention in the end. Okay, so universal object exists in the category for any choice of KMS state tau at the critical inverse temperature. It can be any, you can start with any KMS state at the critical inverse temperature, and you can prove the existence of universal object in the category that I mentioned. Okay. So again, as I mentioned, so it doesn't really make sense to talk about the quantum automorphism group, because the choice of KMS state is far from unique. So it depends on the choice of KMS state. But for strongly connected graph, however, it makes sense to talk about the quantum automorphism group. And nonetheless, one can compute the universal object in the category from the quantum group perspective. At least, what if you can have some more information about quantum groups. Okay, and aside, so the objects in the category, that the categories I mentioned, that are not of Kach type. I mean, I won't tell about what is a Kach type in general, but the antipode enjoys a little more than Kach type condition, meaning that kappa of Qij should be Qji star if it is of Kach type. Here it is not quite Qji star, but it is multiplication by some scalar Qji star that one can prove. So this is an aside from quantum group theoretic perspective. Okay, and of course the computation is not easy. The computation of the universal object in the category is not easy. The reason is that one really doesn't, it's very difficult to sort of understand how much restriction one gets from the state preserving property. It's really difficult. From the linear action, I mean, you can work with generators and all, but when it comes to checking, it comes to, I mean, sort of understanding how much restriction one gets from the state preserving property, it gets difficult. But we have made the computations a little easier by introducing an auxiliary category. Okay, so this category is in principle smaller. It's easier to work with in this category, but it turns out that these categories are, these two categories, the smaller category and the larger category, they are actually same for particular graphs, and that really aids in the computation. What is the auxiliary category? Which is really smaller in some sense. So you consider this vector space, the vector space spanned by SISJ star. Take any ij, I mean, take any two edges, EI and EJ of the graph, and consider this vector space, span of SISJ star, and consider this linear function. Not, I mean, this is just a vector space and linear function. We are not talking about the state on the whole system. What is the linear functional? Psi of SISJ star is delta I. You can take that linear function. That is a small technical thing, because this will be actually linearly independent SISJ star in the vector space V2. So we can take this linear functional, perfectly fine, well defined, and then consider the category. This is another category. This is easier to handle, whose objects are CQJs acting linearly on sister gamma, like before. Linear action, we know what we mean by linear coaction, and if it is linear, then one can check that linear coaction actually preserves this vector space. Then it makes sense to talk about whether this linear coaction preserves the linear functional or not, because this preserves the vector space, so we can hit the linear functional on this vector space. And now you consider the category denoted by C gamma psi linear, whose objects are CQJs acting linearly on sister gamma, and preserves psi on V2. That is the category. That is a restrictive category. But it turns out that for a regular graph, this is a particular choice of graph, but fairly large class of graph, regular graphs. These categories, two categories, C tau psi lin and the original category that we introduced, that we are interested in, that coincide for a particular choice of KMS step tau. Okay, so the upshot is, for that KMS step tau and for regular graphs, the computation is much easier. One has to look, one has to really find the universal object in this restrictive category, and the computation is, I mean, easier because this is far restrictive. The category is far restrictive. Okay, and it can be proved, and it was actually sort of observed earlier in a paper that this category C tau C gamma tau KMS contains this the quantum automorphism graph of the underlying graph, okay, not graph system, the underlying graph, and as well as free product of circles, they are contained in this category. The thing that was observed, that these two objects, the quantum automorphism group of graph and free graph, actually coax on graph system. That was observed, but it was not observed that whether that coaction also preserves that particular choice of KMS state. That was not observed. That we observed that it also preserves the particular choice of KMS state where these two categories actually coincide. And so in that sense, the universal object is quite large. It contains these two sub-objects. Okay. Okay, so let's look at some of the computation. Let's mention. So Kunj algebra with n generators. This is an example of graph system algebra, and it has a unique KMS state. So it makes sense to talk about the quantum automorphism group at the critical inverse temperature, right? Because this has a unique KMS state at the critical inverse temperature, and this turns out to be the quantum unitary group that I mean mentioned in the beginning, UN plus. Okay. And if you take complete graph with two vertices, like this is a complete graph with two vertices without any loop, then it turns out the you can have a KMS state like it has two vertices. So if you take the probability measure to be half on the vertices for this particular choice of KMS state, the universal object turns out to be quantum doubling of free product of two copies of circle. Okay. And what is the most interesting example, let's say, is that if one considers n vertices with each vertex having only one loop, that I already mentioned this graph, that this is the graph that you take n disjoint vertex and each vertex having a loop, then it has infinitely many KMS states at the critical inverse temperature 0, and each coloring of the vertex gives rise to a class of KMS 0 states. So you can guess like the probability simplex in the set of vertices. So each coloring will give rise to a class of KMS 0 states. So what we have proved, this is the result, that if you have a partition of n or equivalency coloring of n, that will give rise to a class of KMS states. Let's say the class of KMS states by tau. You take a class corresponding to that partition, take any KMS state from that class, and the quantum automorphism group corresponding to that state, or let's say the universal object in that category corresponding to that state tau, turns out to be this object. This is a free product of free rate product of Z with SMI plus. This is, I mean, quantum permutation group on Mi symbols. Okay, and this has resemblance with some other results in the literature also, like for graph also. If you talk about only quantum automorphism of group of graphs, this result actually holds true. That was done by Bishop, but we could not do it for taking like disjoint copies of strongly connected graph. Like we have this disjoint copies of one loop, say. So one would like to have the result by replacing these loops by any strongly connected graphs and try to get some analog of this result, but we could not do it till now. And as a particular case of this result, if one take the partition to be 1 1 1, meaning that you take the probability measure, you assign 1 by n if you have n vertices. So at each vertex you assign 1 by n, that will give you a probability measure on the vertex. Then the quantum automorphism group, meaning that the universal object in that category, that turns out to be a unitary easy quantum group H infinity plus. So this is quite interesting because these easy quantum groups, which are really sort of some quantum groups in this tower, not only that, this is Sn and this is Un plus, the quantum unitary group. It is somewhere in that tower, and not only that, its co-representation category is actually given by some bicolored partition. Okay, so this is a quite interesting class of quantum groups and quite well understood class of quantum groups, I would say rather. And so one of them has been realized as a universal object in some category. So that is quite interesting. And this is the, I would say, the most interesting computation that we have so far. Okay, so this is about the computation of universal object in that category. And we had some other consideration also. So once we know that for any graph sister algebra sister gamma, you have a graph, this odd plus gamma, the quantum automorphism, always coacts on sister gamma, right? that we know that somebody else had observed. So I'll mention the reference maybe. So once we know that, then it makes sense to talk about the invariance of a KM state under such coaction, right? So there are plenty of KM states we know for graph system algebra. It is quite different from MNC, that we have plenty of KM states. So now it makes sense to talk about, okay, how about invariance of such KM states under some natural symmetry, like on sister gamma, the underlying group symmetry of the graph will coact on sister gamma, and also underlying quantum symmetry of the graph, underlying graph, that will also coact on the sister gamma. So what can we say about invariance of KM states? Okay, so now we have three different scenarios. I'll quickly mention three different scenarios that sort of sums up the things in this direction. So if you have strongly connected graph gamma, we have already mentioned that then the corresponding graph sister algebra sister gamma has a unique KM state, right? And it turns out that the unique KM state is invariant under the coaction of OT plus gamma. Okay, so that is interesting, that it is automatically invariant. And for a circular graph, if we change our graph and we take a circular graph, then for a particular circular graph, we can prove that the sister gamma has infinitely many KM states at the critical inverse temperature in general. It will have infinitely many KM states, but there is only one group invariant KM state. And if it is a group invariant, then it has to be quantum group invariant also. That is easy result. It is not difficult, but I will mention that. So this is the second scenario, and the final scenario is that we have an example of a graph such that sister gamma has infinitely many KM states at the critical inverse temperature, and all of them are invariant under the action of automorphism. And what is interesting is that there is a unique quantum automorphism group invariant KM state at the critical inverse temperature. So in that sense, we can see that the quantum symmetry is quite rich in this regard also. Not only like we have already seen that it is rich in that sense because Sn plus is quite large compared to classical Sn, but in this regard also we see that it is quite rich. I mean, in some sense that it I mean demonstrates the richness of quantum symmetry. And how we did that very quickly, I can tell that the quantum vertex transitivity of OT plus gamma, we know what is quantum vertex transitivity. This is quite different from vertex transitivity, but this is proved fairly recently that the quantum vertex transitivity and vertex transitivity are really different concepts. A priori they are different, but it was not known that they are different, meaning that do we have some graph which is quantum vertex transitive but fails to be vertex transitive? And such an example was actually given by I will mention the reference, and it turns out that the invariance of KM states, it is quite intimately related to the quantum vertex transitivity or vertex transitivity of the underlying graph. Again, as I mentioned in the beginning, that the underlying combinatorial object really helps in studying the corresponding sister algebra. So exhibiting the last example ultimately boiled down to find such a graph, and it was already found. That graph was already found. Our contribution was to establish that quantum vertex transitivity is the thing when you want to study the invariance of K states. Okay. So okay, yeah. So these are the, and let me tell some of the future direction that one can pursue. I think that to realize the unitary easy quantum groups as the quantum automorphism groups of graph system algebras, like we have already Hn infinity plus, but given any unitary easy quantum group, can we realize it as universal object of some category of CQGs coacting on graph system algebras? It looks a little difficult, because that will mean that you have to have Sn as a symmetry of the edges. That is one requirement, that it puts restrictions, severe restrictions. So let's see what we can do about it in the future. And also what I have not mentioned, that we did something like for the Cooney algebra, we had introduced what is called an orthogonal filtration, and it turned out that the universal object in the orthogonal filtration preserving category and our category turns out to be same. But it would be interesting to see that same can be done for a general class of graph system algebra, what are called Kunz-Krieger algebra. I will elaborate on that. What is Kunz-Krieger algebra, and of course the generalization of the free base product thing. What we got for disjoint union of loops, can we generalize for disjoint union of strongly connected graphs also? So these are some of the future direction one could pursue in this topic. So these are references. So this is the reference where they have found. I mean, they used game theoretic technique to find quantum vertex transitive, but not vertex transitive graphs. That was the first of such kind. So that was interesting. And these are the papers or the preprints that I mean, from these preprints or papers I have prepared the talk. So these two papers, these three papers in fact, and this preprint. And for graph algebra, graph switch algebra, this kind of thing, this is a good reference of relevant graph algebras. And the quantum symmetry of graph system algebra previously was studied, but in a slightly algebraic way, let's say algebraic way, by these two people, Mead and Weber. You can look at this paper also to get a little more algebraic flavor. Okay, thank you.
Okay, thank you for the insightful talk. And so let me ask anybody in the audience if they have any questions, please ask.
Soumalya, thanks for nice talk.
Oh, thank you.
Yeah. So I have a small question that so is the quantum symmetry of the graph sister algebra, is it generated by as a sister algebra by the free product of circles and the quantum automorphism of the graph in general, or do you think it's...
we have not looked at it.
No. So what do the examples say? For example, the examples you have computed, in this case, does it happen? Because you said these two things are contained there.
Right, so, but it doesn't look like, I think.
It doesn't look like, okay, that's what it doesn't look like. So it could be still bigger. It seems like still bigger.
Yes.
Which is good, and which is a better news. Okay. That's on the idea.
Okay, thank you.
So there was a question in the beginning by Rohit where he asked that whether the graph is also row finite. Probably in the first part of your
our graph is finite graph, so it is
graphs are finite, so it's
finite.
Yeah, sorry.
Yeah. For row finite graph, the problem will be the underlying sister algebra won't be unital. So
sure. No, I realized it later that the graphs are finite, so it's a vector space. Yeah.
Yes.
Anyways, thank you.